Hello viewers, welcome to another lesson on probability. Today we will discuss total probability and also introduce you to the concept of Bayes theorem. Let's start with the situation. Suppose you have two bags, bag X and bag Y. We select a bag and from the selected bag we draw a ball. Now, bag X has 3 green and 4 red balls, bag Y has 2 green and 5 red balls. Now, what is the probability that the ball selected is, say, a green ball? So far you have been dealing with situations where we had only one bag and you can have 2 or more color balls in it. So, what changes now? You may select bag X and then draw a ball out of it, or bag Y and then draw a ball out of it, which may be green is what you are looking at. So, we want to find the probability of getting a green ball from bag X or probability of green ball from bag Y, and therefore, the probability of a green ball drawn at the end of this experiment will be the sum of the two probabilities, that is the probability of green ball from bag X and the probability of green ball from bag Y. Now, what is the probability of the bag X getting selected? So, what is the probability of bag X getting selected? Considering bag X and bag Y to be equally likely to be selected, bag X probability is 1 by 2, bag Y probability is also 1 by 2. Getting a green ball from bag X is 3 by 7, because 3 green and total number is 7. Whereas, for bag Y it is 2 green and total 7, so 2 by 7. What we have learned earlier is something called as multiplication theorem, which tells us that the probability of a green ball from bag X is same as the product of the probability of bag X and the probability of green, given that the bag X has been selected. So, it is half into 3 by 7. Similarly, green from bag Y is half into 2 by 7. And therefore, we are ready to say that the probability of green ball, which now using the assumption that X represent bag X being selected and so on, the probability of green ball becomes probability of X into probability of green ball, given that bag X was selected, plus probability of Y into probability of green ball, given that the bag Y was selected. So, what you now need to do is just plug in the values as we found out in our earlier slide, and the total answer is ready as 5 by 14. Now, this is a kind of a situation we will now extend in our next situation. So, look at the problem and see what it says. We have a fair die being rolled. If one turns up, a ball is picked up at random from bag A containing 3 red and 2 green balls. If 2 or 3 turns up, a ball is picked up from bag B containing 3 red and 4 green balls. If 4, 5 or 6 turns up, then the ball is picked from bag C, which has 4 red and 5 green balls. The die is rolled, bag is picked and a ball drawn. What are the chances of drawing a red ball? Now, in this situation, the selection of the ball depends on what the die shows. In this case, the selection of the bag depends on what the die shows, and therefore, you have to consider possibilities. What if die shows 1, or what if the die shows 2 or 3, or what is the possibility of the die showing 4, 5 and 6 leading to? Let us take a look at it in a diagram form. Usually, we call it as a tree diagram. So, we kind of branch out all the possibilities, and that puts the entire picture in a very concise manner for you. So, what if the die shows 1? What would we get? We will pick a ball from bag A, which contains 3 red and 2 green. If the die shows 2 or 3, we pick a ball from bag B which has 3 red, 4 green. If we get 4, 5 or 6, then the ball is picked from bag C which has 4 red and 5 green. And then we are looking at the probability of a ball coming out of each of these selected to be a green ball. Now, in this case, the probability of bag A is same as getting a 1 on the die. Therefore, the probability of A is 1 by 6. Probability of bag B will become 2 by 6. Probability of bag C is 3 by 6, because 4, 5 or 6 can show up in 3 favorable ways. Probability of bag C will therefore be same as probability getting a 4, 5 or 6. And getting a red ball out of the bag A, the probability therefore will become 1 by 6 into 3 by 5. So, 1 by 6 is probability of the bag A into probability of a red given that bag A was selected. Similarly, probability of a red from bag B will become 2 by 6 into 3 by 7, and red from bag C will become same as 3 by 6 into 4 by 9. And therefore, the total probability of the red ball is same as per the expression here, which individually has been evaluated, and if you plug in the values of each of these corresponding probabilities, you get the final answer, and therefore, the probability of red ball is 293 over 630. Now, this is exactly what we are referring to as the total probability, that is not only of one possibility, but covering all the possibilities of the experiment which leads to a final outcome. You need to cover for all the possible events that may have occurred. We have a general result which summarizes what we have just discussed. Let us note down what the theorem of total probability suggests. Theorem of total probability says that if E1, E2, E3 up to En are partitions of the sample space. Partition is a term which we are introducing right now. So, let us take a look at what partition means. Events E1, E2, E3 up to En represent a partition of the sample space if they are pairwise disjoint, exhaustive and have non-zero probabilities. So, there is nothing common between event E1, E2 etc., and they exhaust all possibilities and they have non-zero probabilities. In this previous example, in context of the previous example, E1, E2, En would be nothing but selection of the bag 1 or the bag 2 or the bag 3. A will be the probability of a red ball being selected. That could have come from either of the 3 bags. And then the result says that the probability of A, that is of the red ball or green ball as our previous examples, will be same as the sum of the product of individual events probability and the probability of event A given that EI has happened. So, it can be written as P of E1 into P of A given that E1 has happened, plus probability of E2 into probability of A given that E2 has happened, up to the number of times that events are possibly happening in this experiment. In short, it can be written as summation of P of EI into probability of A given that EI has happened, summation running over 1 to n. This is something which looks complicated, but if you have understood our previous 2 examples, then this would make sense. Now, let us talk about another very important theorem known as Bayes' theorem. Bayes' theorem in probability is as important as Pythagoras' theorem is in geometry. This statement or result was originally discussed and stated by Reverend Thomas Bayes. At present, the result is widely used It's found its usage in topics ranging from marine biology to development of spam blockers for email systems. Let's consider the theorem. What does the theorem state? And then we will talk about its applications as well. The Bayes theorem states that if E1, E2, E3 up to En are partitions of the sample space S and A be any event of non-zero probability associated with S. So, these are the same things that we talked about in the total probability as well. Then probability of EI given that A has happened. So, what is the probability of bag X given that a red ball was taken out is same as probability of EI into probability of A given that EI has happened divided by summation of probability of EI into probability of A given that EI has happened, summation running from 1 to n. And this is true for any I taking values from 1, 2, 3 or n. Now, this result has a very close association with two things that we have talked about. One called the conditional probability, other multiplication and total probability, which we covered today itself. A quick short proof will put things in a correct perspective for you. Why and how do I get this result? Simply because the conditional probability tells us that probability of EI given that A has happened is same as probability of A intersection EI divided by probability of A. And what is probability of A? The denominator, the total probability, because A is associated with E1, E2, E3 or En, events which are partitioning the entire sample space. And therefore, I replace P of A in the denominator by summation of Pi into P of A given that EI has happened. Whereas, the numerator can be by conditional probability be replaced by probability of EI into probability of A given that EI has happened. I think if we take our one of the examples that we discussed earlier and turn it around, it will give you a better understanding of Bayes theorem. Let's get back to the example where we have bag X and bag Y. 3 green, 4 red in bag X, 2 green, 5 red in bag Y. One bag is selected, ball is drawn. What we now know is that the ball drawn is a green ball. What is the probability that it has come from bag X? So, we are interested in finding the probability of what must have happened in the first stage of the experiment. First stage where the bag is selected, second stage is where the ball is drawn. So, we now know what color of ball we have got. We want to know what is the probability that the ball has come from bag X. So, using Bayes theorem, we know that the probability of X given that a green ball was drawn out is same as probability of bag X into probability of a green ball given that bag X was selected divided by probability of X bag into probability of green given that bag X was selected plus probability of Y into probability of green given that Y was selected. We know individual probabilities of all of these quantities. So, I have half into 3 by 7 divided by half into 3 by 7 plus half into 2 by 7. Just simplify and it becomes nothing but 3 by 5. And therefore, probability of bag X being selected given that a green ball was picked is 3 by 5. And therefore, the Bayes theorem helps us to find probability of an intermediate possible outcome, the outcome of bag X being selected when you know that at the end of the experiment a green ball was picked up. So, this was one of the applications of Bayes theorem. In our next lesson, we will take some more applications of Bayes theorem. See you in our next lesson.